So before we left for the break, we were looking at phase diagrams and for pure components. And the canonical pure fluid phase diagram for water is of this form. And we actually went through a whole discussion of why these phases can arise, or how we can rationalize and predict using some level of quantification how these levels arise through the use of the chemical potential and the notion that the chemical potential is minimized for a pure fluid at any given combination of state conditions such as pressure and temperature. Okay, so we also then moved on to generating this idea of degrees of freedom, meaning how many independent variables can we specify in a system and have that system be in a phase that we would like it to be in. So for instance, in the case of a single pure fluid, right, we can specify two components or two independent variables if we want it to be in a single phase system, such as solid, liquid, and vapor. And this was behind this thing called the Gibbs phase rule, which we derived. So it's really not a rule, it just is a manifestation, really. It's the result of the first and second laws, really. So it's really not a rule. And it told us that the degrees of freedom that we are allowed to vary independently for a system is 2, let's see, plus C minus pi, where C is equal to the number of components and pi is the number of phases. Okay, so C equals the number of unique or independent or distinguishable chemical components. For species, and then pi is equal to the number of phases. And so we see at a triple point, for instance, in the case of a fluid, we have C is equal to 1 because it's pure, pi is equal to 3 because we have 3 phases. And so the degrees of freedom should be 2 plus 1 minus 3, which is 0. And that makes sense because we don't really have any degrees of freedom to specify the triple point, because that's a point and it's determined by the fluid. Okay, so that's something that is what it is, and why it is beyond the scope of science. Okay, so let's go on and sort of lead to something that's kind of interesting. And I'm not gonna, we'll return to this, but this is connected to the idea of degrees of freedom in terms of the Gibbs phase rule. And if you have, let's say, a system at a particular temperature and pressure, okay, and we have liquid and it's in equilibrium with a vapor, but this time we're gonna have 2 species in each of the liquid and vapor phases. So we have a species A and a species B in the liquid, in the vapor, and likewise. Okay, so we know that we can now specify temperature, pressure. We could actually also specify the mole fractions of each of the species in the liquid and the vapor. And so liquid mole fractions we label as X and vapor as Y. And we know that the mole fractions are connected because YA plus YB has to equal 1, and XA and XB added together have to equal 1. So really, again, in this kind of a system, which is called a binary phase equilibrium, where we have 2 components, binary, and we have 2 phases, liquid and vapor. If we wanted to sort of consider the degrees of freedom, right, naively, right, we would say that we could actually, even though I said we have a system at a particular temperature and pressure, we could opt to let temperature and pressure be variable, right? We don't have to set them to anything. We might say, all right, well, temperature and pressure are independent variables. That's not really hard to envision. We can say that we can specify those. We could actually specify YA or YB, and we could potentially specify XA or XB. And remember, the B component mole fractions are just one minus that XA or YA. So we don't really have to specify. We can't specify them both, right? We don't have that degree of freedom. That's why it's only the mole fractions of one of the species in the system. And so naively, we might think that these are the kinds of variables that we could manipulate independently, okay, without them affecting anything, right? So I could particularly specify temperature, pressure, and the mole fractions. But if we seek recourse in our Gibbs phase rule, okay, which tells us that the degrees of freedom we have for a system like this is 2 plus c minus pi, okay, that tells us that it's 2 plus c, c is equal to 2 because we have a binary system, and then pi is 2 because we have two phases, the liquid and vapor, and that tells us 2 plus 2 minus 2 is equal to 2. So what this is telling us, as opposed to our naive view of how many degrees of freedom we have, which we could have thought, or we would have thought naively to be 4, okay? Turns out if we use Gibbs phase rule to be 2. In fact, we have half as many degrees of freedom, okay? And this is interesting because let's say you choose temperature and pressure as your 2 degrees of freedom. And it's quite plausible that you would want to choose temperature and pressure because that's something you can control. So if you take temperature and pressure to be your 2 degrees of freedom that you say, all right, well, I'll just specify those, right? Pressure is 1 bar and temperature could be whatever you want, 300 Kelvin, all right? What that tells us then is something very interesting, and that is that once you specify pressure and temperature, YA and hence YB, and XA and hence XB, because XA, remember, we have sum of the mole fractions has to equal 1, are determined. You have no degrees of freedom. You have no freedom in specifying the mole fractions or the compositions of the fluids. Now, this is actually, if you think about that, this is pretty remarkable. So you have 2 species, A and B, right? And let's say, as a chemist, you run some reaction and then, luckily at the end of the day, you only have 2 species in your solution, A and B. And in fact, under the experimental setup that you have, you also have this liquid being in equilibrium with its vapor in some form or another. And both of the species are volatile so that you have A and B both in liquid and vapor. But what this means is that if you're careful enough to conduct your experiment or your synthesis or whatever you're doing at a particular temperature and pressure, which most likely you would be controlling those things very carefully, the compositions of those 2 phases are determined for you. You have no choice. And that's pretty remarkable if you think about it. Right? Whatever's there is there. Here I have no, I'm not talking anything about the stoichiometry of a chemical reaction. I don't even have any sort of chemical transformation here. This is pure thermodynamics. And what it's saying is that once you specify temperature and pressure for this particular type of system, which is a binary liquid vapor system, binary 2-phase system, your compositions are determined once you specify temperature and pressure. And that's pretty remarkable because if, let's say, one of your components, B, is again a high value product from your chemical reaction, right? And you want to have that in a particularly high concentration, in either phase, right? Well, you're stuck to whatever the experimental conditions allow you to have it be, right? And that's pretty remarkable. So being able to predict these types of equilibria is non-trivial, particularly when you're looking at this from an economic and a commercial point of view, where one of the things you're making, and most likely you're making it because it has some value, and you want whatever you're making of value to be in high concentration. You need to understand, or at least ahead of time, know what sort of compositions your system will have in order to be able to design a process. Okay, so this is a prelude to when we get to binary phase equilibrium a little later. Okay, and I thought that's quite interesting, and it's a nice place to point this out in terms of the degrees of freedom. Okay, so now I'm going to move on and go back to this phase diagram for a single system, okay, for a pure fluid. And the question I want to ask, if there's no comments or discussions at the moment, is how to describe these lines. Okay, so in these phase diagrams for pure fluids, you have these two-phase or coexistence lines, okay, curves. Okay. And so we want to address how we would describe those. And in particular, we want to know the rate of change of pressure as a function of temperature along these lines, because once we obtain the derivative of these lines locally, right? And so we can get expressions or quantify the rate of change of these curves at any point, right? In terms of some variables of a system. We can then find relationships between pressure and temperature at any point along those curves. And so we'll see that in a moment. So let's go back and just draw it here. So let this be phase alpha. This is phase beta, and this is phase gamma to keep things general, okay? And what we want to know, the question is, what is dp dt at the coexistence line? Okay, so what we want to know is what is the slope, right, of these curves. So that's what this means. What is the slope dp dt, because this is a graph of pressure versus temperature, so the slope is just dp dt, the derivative. And we want to know it under conditions of coexistence, and it could be coexistence of alpha, beta, or beta gamma, or alpha gamma. Okay, those are the two phases. So that's the question. And so to answer this question, we're going to rely or go back to thermodynamics. And we know from thermodynamics, okay, so the solution or our answer to this question begins with thermodynamics, obviously. We know that mu, since this is a pure fluid, right? So this is a pure fluid, that mu in the alpha phase, let's say we're dealing with alpha and beta for the moment, okay? So solution for alpha beta coexistence. This will apply to any of the combinations, okay? Alpha gamma or beta gamma as well. We know that along these lines, mu alpha, so the chemical potential of a molecule in phase alpha is going to equal the chemical potential of a molecule of this fluid in phase beta. Okay, that's from thermodynamics, and we showed that already. So if we start at this point, we know that the chemical potential of a molecule in either phase is going to be equal. Okay? If not, then we would only have one phase in existence. If a molecule had a lower chemical potential, meaning a lower free energy in phase alpha, right, then all of the molecules would move or want to be in a phase that is like alpha, because then you're maximizing or actually minimizing G, which is what we want from thermodynamics. G is minimized in an equilibrium state. But at coexistence, the Gibbs free energy per molecule or per mole has to be the same in both phases. Otherwise, you would have a phase change, okay? An irreversible phase change. So mu alpha is equal to mu beta. Now, if we move along this line, right, and we know that mu is a function of pressure and temperature, and since this is pure, we can just say this is a function of pressure and temperature. Okay, so if we start at a particular combination of pressure and temperature, okay, that's P1, let's say, and that'd be T1, and we move along the coexistence line because that's what we're interested in, this coexistence line. Okay, so we move in this direction, okay, And so we hit this point. And this line is not vertical. I really should not have drawn it that way, huh? I should probably draw it this way. Okay, so we start here. Okay, and then we move along the line. And then we end up here at this point. Okay, so now our new pressure and temperature combination is P2 and T2. So we had a change in pressure and temperature along those directions. So if that's the case, right, we know then that mu alpha at 0.1 is equal to mu beta at 0.1. We also know that mu alpha at 0.2 is equal to mu beta at 0.2. Okay. Does that make sense? It has to be because we're at the coexistence line and we're still having no differences in chemical potential. So if I take the difference, mu alpha 2 minus mu alpha 1, right? If I subtract the two equations, that's the same as saying mu beta 2 minus mu beta 1. And that's because mu alpha 2 is equal to mu beta 2, right? So that these two are equal. And mu alpha 1 is equal to mu beta 1. So all I've done is write an equality that stems from these two equivalences of the chemical potential. Okay. Now, if P and T change by infinitesimal amounts, dP and dt, okay, then mu changes, mu alpha and mu beta change by d mu alpha and d mu beta. Okay, and so these differences that I've shown here, okay, become differential or infinitesimal changes if those pressure and temperature changes are very, very small. What that lets us write then is d mu alpha is equal to d mu beta. Okay, that's what that lets us do. Okay, any questions? So the differential changes along this line, okay, in the chemical potentials of a molecule in both phases has to be the same, because you're going to stay on this line, and along this line, the chemical potentials are always the same in both phases. So if there's any change, those changes have to be the same for both phases. Otherwise, you would be out of sync. Okay? And so that's all this is saying. This is rather a trivial result. That the changes in the chemical potential, the differential changes in chemical potential have to be the same in both phases. Now, for a pure fluid, we know that d mu is just v bar dp minus s bar dt. Okay, this is just something that we've already seen before. So we can use this expression and write it in terms of the two phases. Okay, so we're going to use this expression and plug it into this thing in the box, which is the differential for the chemical potentials. So that gives us V bar in phase alpha dP, right, which is this coexistence pressure. So we'll write this as dP coexistence minus S bar of alpha dt coexistence is equal to V bar beta, okay, dP coexistence minus S bar in phase beta dt coexistence. And so this is equal to that. Okay. So we see here now we have these terms, dP coexistence and dt coexistence. We're going to combine those. We're going to collect things that are associated with those terms because we want dP dt. So let's see if we can combine things that belong to dP and things that belong to dt. Okay. So we'll do it this way: V bar alpha minus V bar beta. Okay. So all I'm going to do is bring the V bar beta from the right-hand side to the left. That's why I have a negative. And that's going to be dP coexistence. Okay. And then I'm going to bring the S's on to the right-hand side of the equal sign. So there I'm going to have, let's see, S bar alpha minus S bar beta times dt coexistence. Okay, and that's just a simple rearrangement there. And then all we do is collect dp dt. We can divide through by a few factors to get dp dt on one side. So we get dp dt at coexistence is equal to S bar alpha minus S bar beta divided by V bar alpha minus V bar beta. Okay, which is really just delta S bar, because that's a delta S to go from phase alpha, to go from phase beta to alpha. Okay, so that's the entropy change for a phase change where you have something going from phase beta to phase alpha, right? Final is alpha, initial is beta. And then on the bottom, you have delta V bar for the phase change, again, where you're going from beta to alpha. And that's all it is. So that's what this intermediate result is, that the slope is really related to the changes in entropy and molar entropy and molar volume for pure fluid. Okay, so again, this is at coexistence. So this relationship, this very general relationship, it holds along this line, and along this line for a pure fluid. Okay, any question? All right, so let's move on. So let's see, so this is very general. So we're gonna now sort of see where we can go with putting in some more details for it. So at equilibrium, we know at phase equilibrium, right? So let's say we have, here's phase alpha and here's phase beta, and here's, let's say, a molecule in phase alpha, right? And here's the same molecule in phase beta. We know that mu alpha is equal to mu beta, but for a pure fluid, this is just equal to G bar. So G bar alpha is equal to G bar beta. Okay, that's all this is. But we know what G is from its definition of G. Recall G, which is equal to H minus Ts. Okay, so G bar is equal to H bar minus Ts bar, where T is temperature and everything with a bar over it is a molar quantity. So we can write, let's see, at equilibrium, G bar alpha is equal to G bar beta, okay, which means that delta G bar is equal to 0 at equilibrium for a phase equilibrium. So here we're going from beta to alpha, let's say. Right? So that was the phase change that we were looking at here, from beta to alpha. Okay. So delta G to go from beta to alpha is 0. And that's just our thermodynamic result. Okay. So we know that G bar alpha is equal to G bar beta. So this is just H bar alpha minus T times S bar alpha is equal to H bar beta minus T S bar beta. So we collect all of these things that we can. H bar alpha minus H bar beta is equal to, let's see, T times S bar alpha minus T times S bar beta. Okay. And we know that this T actually is coexistence temperature, because we're talking about coexistence. So I'm going to put in coexistence. Okay. So this is just delta H bar to go from beta to alpha. That's what this guy is. Okay, and on this side, we have T coexistence times S bar alpha minus S bar beta, which is just T coexistence times delta S bar to go from beta to alpha, right? So we can solve for this delta S, right? Delta S bar to go from beta to alpha is equal to delta H bar to go from beta to alpha divided by T coexistence. And why do we want delta S beta to alpha? Well, we just saw here that it appears in this equation right here. Okay, so now we have an expression for delta S bar for this transition between phases. It's given by this guy. And now it's in terms of things that are actually measurable directly, delta H for a phase transition. Okay, so we can put this result back in for our expression for dp dt, which is dp dt at coexistence is equal to, let's go back. This was delta S bar over delta V bar, remember where this blue arrow is? So delta S bar is just delta H bar to go from beta to alpha over T coexistence times delta V bar for the phase transition. And there you have it. This is what we have for our result for what the slope is along this line, all those coexistence lines. It's related to the enthalpy that's associated with the phase change, as well as the change in the molar volume that's associated with the phase change. So as an example, let's say alpha is equal to solid and beta is equal to liquid, right? So now here you're going from beta to alpha, so you're going from liquid to solid. This is a process that's called, as freezing, right? So let's see what we get here. We have then delta H bar is going to be liquid to solid, the enthalpy, the molar enthalpy for freezing or solidification. Okay, and this is going to be less than 0. It's going to be negative. If you want to go from liquid to solid, you're going to have to extract energy from that liquid. Okay, and then delta V bar to go from liquid to solid. Usually things contract, and so this is also going to be less than 0, except for ice in a very special range of temperatures. But these two conditions hold for most substances, okay, except for water, which has a special thing because of its hydrogen bonding. Okay, so we see here then that dp dt along coexistence is going to be greater than 0. Okay, so what this is saying is, for most substances, okay, so this is our solid. Okay. Since dp dt coexistence, to go from liquid to solid, or we can use this to mean liquid solid equilibrium, this slope is going to be positive. That's what this is saying. So here's our solid, here's our liquid, here's our vapor. Okay, our result here from this expression, okay, is saying that the slope dp dt along coexistence, because delta H and delta V are going to be positive, in the case of solidification, are going to be positive, negative, this is going to turn out to be a positive slope. And that's exactly what we see for most fluids. Okay. In the case of water, okay, water is this, and I think some of you may recall, I've been using water as the example. I've been drawing that line in the phase diagram this way, with a negative slope. And I'm exaggerating this line this red line. I'm exaggerating it. It's not that, it doesn't have such an exaggerated slope. Okay, but for water, okay, delta H vaporization, solidification, where we have now, let's see, we're going from liquid to solid. This is still going to be negative. Okay, this is still going to be negative because to go from the liquid to the solid, we have to extract energy. So the enthalpy, the molar enthalpy for this process is going to be negative. But within that certain range of temperatures, very close to the melting point, delta V bar for water is going to be positive. Okay, right? And we know this because ice floats in water. And so ice is less dense. So, and molar volume is a proxy for density. So the change in the molar volume to go from liquid to solid is positive. The molar volume for the solid is larger than the molar volume for the liquid, meaning that ice, solid form, in this very narrow range of temperatures is less dense than the liquid form. And this is why water is an exception. And there are many, many theories as to why this is, all hinging on the fact that water can hydrogen bond and form this interconnectedness. Again, this is something that one can attribute to hydrogen bonds, but it's still widely debated and theorized about. We don't know exactly. Okay, so if we know this for water, then we know that dp dt at coexistence, which is equal to delta H for the liquid to solid transition, times T coexistence, delta V bar for the liquid to solid transition. We see then that this is negative. This slope is negative because this guy has a positive sign, but this guy has a negative sign. And so the slope, and T of course is absolute temperature, is always going to be positive. And so that's why in the case of water, we obtain this red curve, which has a negative slope. Okay, water is the exception here. And there's, I think, silicon or one of those group 4 elements in the liquid phase. Okay, so I think that's pretty cool that our analysis of this behavior of the slope of these lines actually mimics what we see in terms of actual experiments in reality. Okay, so it's all related to some things that are measurable, right? It's related to this and this. So this is actually quite cool that it turns out that way, I think, right? You wouldn't think that these slopes are related to changes in the enthalpy and the molar volume, molar enthalpy and molar volume upon phase transition. But it is, and in fact, because water has this difference, this observed difference in its density that is contradictory, or at least the opposite to what most substances display, we actually can predict that its slope on a phase diagram of pressure versus temperature would have a negative slope, would be negative. So I think that's pretty cool, right? That it actually comes out that way. And all those results are all embodied in analysis of this expression right here in the box at the top. Okay, any questions or comments or discussion? Okay. Okay, great. So let's go on and further look at this expression here. Okay, we're gonna put the expression in the box, and now we're gonna apply it not to a solid liquid transition, but to a liquid vapor transition. Okay, because we're gonna transition into liquid vapor systems after we finish this. So let's take a look at a liquid vapor system. Let me remind you again, dp dt at coexistence is equal to delta H, which is the molar. Now this time we're going to go from liquid to vapor. for a pure fluid, liquid to vapor, okay? And so beta going to alpha is going to be liquid going to vapor, okay? So delta H bar, liquid vapor divided by T vaporization, because this is going to happen at T vaporization times delta V bar to go from liquid to vapor. Okay, so that's what we have as our expression in the case of liquid vapor equilibrium. Okay, so this transition from liquid to vapor still is an equilibrium situation. We're not looking at anything that's non-equilibrium. And so we can actually say that, all right, well, we have a vapor, so that means we have a gas. Okay, so let's first consider this delta V term for our system. So in this case, right, we have liquid, vapor, okay, and we only have one species, so that's A, okay, in both cases. So we need to first consider delta V bar for the liquid to vapor transition. Okay. What we're going to say is that the V bar of the vapor is much, much greater than V bar of the liquid. Okay, and so what that means is the volume per mole of the vapor, the gas, yeah, is usually much, much larger than that of the liquid, right? Liquids are much more dense than gases, and so they have a much smaller molar volume than vapors. So what this allows us to do, it allows us to make an assumption. Okay. So this experimentally observed result allows us to make an assumption in our theoretical formalization or formalizing of this, that delta V bar for the liquid vapor transition, right, which is equal to V of the vapor minus V of the liquid, is going to be more or less equal to the molar volume of the vapor, because the liquid molar volume is much, much smaller. Okay, so that's one, assumption one. So it allows us to make one assumption. So assumption number one, delta V bar, liquid to vapor, is equal to, okay. So that's our first assumption, okay? And now we're going to make another assumption. Number two, vapor is ideal. Okay, so we are looking at the ideal gas equation of state, PV equals nRT. So we have PV is equal to nRT. We know that molar volume is just V over N, which is equal to V bar. And that's going to equal RT over P. Okay, and so this is now our V bar of the vapor, which is equal to V bar ideal gas, because we assumed that our vapor is an ideal gas. Okay, so now we can put in this result into our expression for dP/dt. Okay, so in the case of a liquid vapor equilibrium, we can actually make some approximations here. So let's go back to this expression, which is at the top of the screen. dP/dt at liquid vapor coexistence is equal to delta H to go from liquid to vapor. That's what we have at the top, divided by T vaporization. I just shorten it to T vapor times the delta V, but we said that the delta V for this vaporization process is equal to the molar volume of the vapor right here. That was our assumption 1, based on this experimental observation. Okay, and then we said, all right, the V bar of the vapor, we're going to assume that the vapor is ideal. So we're going to take the second assumption and allow V vapor to be written as RT over P. So this becomes RT coexistence over P. Okay. So we do some algebra here. So we get delta H, the P comes on the numerator. And then here we have RT coexistence squared. Okay, so that's what we have. So let me just put this together here. dP dt at coexistence is equal to delta H for the liquid vapor transition times the pressure over RT squared. Okay, so I'm going to drop this coexistence if you, I'll keep it for a moment. Okay. So we know that the pressures and the temperatures that we're interested in are all going to be along the coexistence. Okay. So I'm just going to drop these subscripts coexistence because these describe the line. So everything, so this expression describes the relationship between pressure and temperature along the coexistence line. Okay, and to remind you, that's just pressure, temperature. This is let's use water again, right? So this is solid, liquid, vapor. So we're talking about all pressure, temperature combinations along this line. Okay, so we can drop the subscripts coexistence because now we know that this is what we're going to be dealing with. So that's what I mean when I say this statement right here. Okay. So we can clean this up. dP dt is equal to delta H bar liquid vapor times P over RT squared. Okay. That's just this expression coming down. And then we can do a little bit more massaging. dP over P is equal to delta H bar liquid vapor over R dt over T squared. And there you have it. We have an expression here that has pressure on one side and delta H liquid vapor transition on the other side and temperature on the other side. Okay. Now we can do some a little bit more massaging of this expression. dP over P we know is just d natural log P is equal to delta H bar liquid vapor over R dt over T squared. Okay. Now let's take a few cases. If we assume, or we know experimentally, from experimental measurements that delta H for this transition is, here it comes again, weakly dependent on temperature, right? We can say that delta H is going to be a constant. We can take that to be a constant if we assume this. Okay. And so we can integrate. So the integration becomes rather easy. Okay. So if P goes from P1 to P2, and T therefore goes from T1 to T2 along this coexistence line. Okay. So what we're saying here is that we're going from T1 to T2, and equivalently from P1 to P2, we can integrate our expression, okay? And that's going to be rather simple. The integral from P1 to P2 of D natural log P is going to equal delta H bar liquid vapor over R, since that's a constant, since we assume delta H is weakly dependent on T. The integral from T1 to T2, 1 over T squared dt. Okay? And at this point, we all know that the left-hand side of the equal sign is just log of P2 over P1. And on the right-hand side, we have delta H bar liquid going to vapor over R, the integral of 1 over T squared. But the integral of 1 over T squared is just minus 1 over T. So that's going to be minus 1 over T2 minus 1 over T1, which then turns out to be, if we were to bring out the negatives, let's see, that would be minus delta H liquid to vapor over R times 1 over T2 minus 1 over T1. So natural log P2 over P1 is equal to that. Okay. And this, okay, is known as Clausius-Clapeyron equation or relation. Okay, and so oftentimes this expression is given to you for the liquid vapor transition so that you can predict the vapor pressure along this this coexistence line. This is called the vapor pressure, by the way, for a pure fluid along the red line here. Okay, you can predict the pressure or the temperature given one or the other, and this enthalpy of vaporization along this line, given some conditions. Okay? And the things that you need to know, of course, are some set of initial pressures and temperatures and the enthalpy of vaporization. Okay. What this is also indicating here is that a plot, you could actually plot natural log of P versus 1 over T. Okay, so if we were to plot natural log of P versus 1 over T, this would result in a linear relationship. Okay, this is another way to modify data. Maybe you've done this in the lab or discussed this in the lab, right? So if you were to plot natural log P versus 1 over T, right? Based on the, under the assumptions that we've made, remember that the molar volume of the vapor can be approximated as an ideal gas, and that the enthalpy of vaporization is weakly dependent on temperature, so that we can assume it's constant. You get this relationship of log P versus 1 over T that's a line. And so the slope of that line is going to be negative. It's going to be negative delta H liquid to vapor. Okay. And so if you were to plot this, you might get some experimental points. Right? And it's never a straight line if you do experiments, but you can always plot a straight line. That's a bad here. Let me put some points on this side now. Okay, so that our line makes sense. And so you would get something like this, and the slope, of course, is minus delta H over R. Okay, so this is what a very interesting way to actually obtain delta H. So if you wanted to obtain delta H of vaporization for a particular fluid, you could actually run experiments at different combinations of pressure and temperature where you had phase equilibrium, where you had both phases present, right? And you could plot that data and then do a regression, a linear regression of log P versus 1 over T, where log P is Y and 1 over T is X. And when you do a linear regression on that, you'll get a slope for the line, and that slope is related to the enthalpy of vaporization, or the transition, whatever it may be, whether you're going from liquid to vapor, vapor to liquid, doesn't matter apart from the sign. Okay, so the slope would be this. So that's the Clausius-Clapeyron equation. But of course, again, we know what I want to impress upon you, again, for the, I don't know, the millionth time, is that this expression, this Clausius-Clapeyron expression, if some, I know a lot of educators like to tend to throw equations at you, right? Just think how, if you really only knew, let's see, how to get to this result, right? And you had enough patience and confidence in yourself, right? If you knew from thermodynamics, some very few ideas of thermodynamics, how to get here, and we've actually come to that point, and looking at the phase diagrams and thinking a little bit, you would not have to be told this expression. You could have actually obtained it by yourself. Okay. So again, one of my missions is to enlighten students to understand that equations always come from somewhere, knowing that somewhere is much, much more powerful than knowing the equation. Because there's so much more loaded in knowing where this came from, right? There's so much more knowledge that you need to know, and then you gain by knowing where it came from than by just being told what this expression is, and then trying to use it in a case where it doesn't work. Why? Because the assumptions don't hold. So we've made so many assumptions that go into this expression, right? That when you run into a case where it doesn't work, and you might go to your boss, or you might go to someone who you're working with who knows maybe a little bit more than you, they might actually question whether you know what you're doing or not. And so my biggest concern is going to someone and saying, oh, it doesn't work, right? But I haven't even thought about all of the assumptions that go into something before I actually go and bother someone to say that it doesn't work. Okay. So that's very important to me. And it should be important to you because it's a very careful and systematic way of approaching things in all aspects of life, not just science, but all aspects. Okay, so with that, I'm going to end my discussion for today. If there are no questions, are there any questions or comments on the material? Okay, I think this is very cool, right? So these are applications of thermodynamics, the first and second laws. Okay, great. I wish everyone a great week. And if there are any questions, I'm still here for a little while for my office hour, and let me know. Okay, take care.